Hello, class. This is Mr. Hart, and in this podcast, I want to go over week two of Earth's atmosphere. Okay, and in this part of the chapter, we're going to look at atmospheric layers. Okay, so what you'll find is that in every part of Earth systems, there's something to do with layers. Okay, when we talked about stars, they had layers. The sun had layers, right? The Earth's core has layers that we'll get to. Okay, Earth's atmosphere is the same way. It has different layers. Okay, it's not the same throughout the whole atmosphere. There's different sections, different densities. Okay, that we need to look at. Okay, and so um, we'll come back to this image in a second. But basically, what we need to know is the different layers and the order they go in. Okay, so we do this in reverse because you can kind of think of the Earth as the bottom of the list. Okay, so this is the lowest. Okay, or the lowest to the Earth. Okay, going up to the highest. So first there's the troposphere, then there's the stratosphere, then there's the mesosphere, then there's the thermosphere, and then there's the exosphere. Okay, so this one's closest to the Earth, this one's the farthest away. Okay, so make sure you have that order in your mind, either written or in your mind and written down, so that you can have it memorized. Okay, but the troposphere, then the stratosphere, then the mesosphere, then the thermosphere, and then the exosphere. Okay, you should have that. You need to have that memorized. Okay. So let's go back to this picture. Okay, you'll notice that they're not the same distances apart. Okay, they're not the same thickness. The thermosphere is very large, whereas the troposphere is very small. Okay, so you'll notice these little markings on the side. If you can't read them, it says 11 kilometers. Okay, that's about 7 miles or so. The stratosphere is about 50 kilometers up, or goes up to about 50 kilometers, which is about 35-ish miles. Okay. Then the mesosphere goes up to about 87 kilometers, which is about 55 miles. Okay. And then the thermosphere goes way up to 500 kilometers, which is about 350 miles or so. Okay. And so you'll see that the different distances, if you draw on a scale, this isn't even accurate. The thermosphere would be much, much larger than this, but you can't really draw it on a picture and have it fit on the screen. Okay, but you should kind of have an idea that the troposphere is smallest, then the stratosphere and the mesosphere are about the same size, and then the thermosphere is just ginormous. Okay, and the exosphere doesn't really have a size, and we'll get to that in a second. But the reason it doesn't have a size is that it's kind of the edge of the atmosphere. It doesn't really have a set distance. Okay. But if you look at the atmosphere, this is kind of from a side angle. Okay, kind of think of a satellite taking a picture from the edge of the Earth. Okay, you can see down here. Here's the lower troposphere. This pink part is the stratosphere, and then this part is the upper atmosphere, and then this is the thermosphere. Okay, this upper atmosphere consists of the mesosphere and the thermosphere kind of put together, and then it slowly just kind of dissipates out until it's outer space, basically. Okay, but you can they kind of colorize it so you can see the different thicknesses. The troposphere is definitely the thickest. Okay, and then it slowly dissipates out. Okay. All right. We also want to differentiate between a sphere and a pause. Sometimes you'll hear them called like the stratosphere, and sometimes you'll hear it called the stratopause. All that means is it's a slight difference. The stratosphere means all the air inside that part of the atmosphere, okay? Whereas the stratopause would just mean the boundary line for that part of the atmosphere, okay? So if I go back to this picture, this would all be the troposphere, but this line, this boundary is the tropopause. Then this whole part would be the stratosphere. Then this line is the stratopause, okay, the boundary. This whole part would be the mesosphere. This part would be the mesopause. And then this whole part would be the thermosphere, and this would be the thermopause, okay? So just know sometimes the textbook uses either version, okay? Again, it's a slightly different definition, but just make sure you understand they're kind of referencing the same thing, but one's referencing the whole part of that layer, and the other's referencing just the boundary, okay? So sphere, whole part, pause, boundary. Okay? All right, now let's look at each sphere individually. So the troposphere is the closest to the Earth's surface. Okay, this is where all the weather happens. Okay, this is where clouds form. Okay, and if you think about it, it's Earth's surface is going to be the major source of heat. That makes sense since it's the closest to the Earth. Okay, it gets some heat from the sun, but most of it's that radiant heat off the Earth. Okay, it's the greatest density gases for the spheres, which makes sense since it's on the bottom. And then its temperature decreases with height. Okay, and that also makes sense because if the Earth is its heat source, then the further away it gets from the Earth, the cooler it's going to be. Okay, so that's the troposphere. Then there's the stratosphere. Okay, stratosphere kind of has a popular culture phrase. People will say, "Oh, he shot it up into the stratosphere." It means something very high, but it actually is a layer, right? It's not just a popular culture thing. But its temperature is kind of strange because it actually increases with altitude, okay, instead of decreasing. Okay, and part of that has to do with because its main heat source is the sun, but more of it has to go with the ozone and the greenhouse gases, and we'll get into that later on in the chapter. But just realize the stratosphere is a little bit different, okay, because of this temperature increasing with altitude. And if you think of the stratosphere, it's above the cloud line. If you've ever flown in an airplane, you're usually flying in the upper troposphere, maybe even the lower stratosphere. Okay, so usually above the cloud line is what the stratosphere. That's how I like to think of it. Okay. Then there's the mesosphere. This one it decreases with altitude. The temperature decreases with altitude. Its heat source is the stratosphere, and that's just because it has so few particles. It doesn't absorb the sun's rays. Okay. And so it's just getting most of its heat left over from the stratosphere. Again, very few gas particles at this point, very cold. And this is where meteors actually burn up. So if you ever see a shooting star, you're seeing it burn up in the mesosphere. Okay? All right. And then last of all, there's the thermosphere. Okay? At this point, there's almost no gas particles. There's one every kilometer on average. That's pretty spread apart. Okay, but it's still considered the atmosphere because we can still detect those particles. Okay, and this is known for containing ions, or also known as the ionosphere, because that's where the northern lights are created, or the aurora borealis. Okay, and so this is where we get all those cool colors that you see in Alaska and other things, is in the thermosphere because of that ionization that comes from solar flares and stuff. That's all absorbed in the thermosphere. Okay. And so, again, if you've never seen the Northern Lights, this is what they look like. Really cool, amazing images. Okay, this is my favorite image of the Northern Lights. This is an aerial view, and you can see this ring coming around the North Pole. And if you remember from when we talked about solar flares in the last chapter, you could remember how the magnetic fields kind of created these rings near the top that the solar flares would pour into. Well, you can see that right there beautifully with that ring from the Northern Lights, and the solar flare just feeding into that part of the Earth's atmosphere. Okay, so Northern Lights are just spectacular. Here's a YouTube video I recommend watching. Okay, that just shows some amazing Northern Light features. Okay, but one student actually pointed out that these look really close to us just because they're so big, but again, they're actually pretty far away. The thermosphere is pretty high up, and so this is actually a lot of ionization energy that's causing these lights, and it's spread out pretty far apart for it to look this big in our view. And so it's really quite incredible how big of a feature this is and how high up it is. Okay? All right, and the last sphere is the exosphere, where it's really not a part of the atmosphere. It's kind of just like you can think of it as the crust or the corona like we had for the sun. It's just the point where we say, okay, this is the edge of the atmosphere. This is basically outer space. There's really no more particles at this point. Okay. And so that's why it doesn't have a boundary line, because we really can't say where it stops. It's kind of just letting you know, hey, there's nothing out here at this point. Okay, so that's the exosphere. And there you go. Those are the 5 layers. Okay. And again, we said that the stratosphere had that unique feature of the temperature going up. So if you actually plot the temperature, okay, temperature on the bottom, altitude going up, okay, And so as we go higher and higher into the atmosphere, you would expect it to decrease in temperature, which it does in the troposphere. Okay. But then when you get to the stratosphere, remember we said that increases, which is kind of a strange phenomenon. You wouldn't expect this switching of directions. And then in the mesosphere it goes back, and then in the thermosphere there's not really a temperature because it's so thin. But anyways, just realize that the temperature is not nice and consistent. The higher you go up, the colder it is. That's not always the case because of this strange reverse in the stratosphere. Okay, so just look at that plot for a minute and kind of get a feel for what's happening. Okay, so it gets cold in the troposphere, but then it gets cold in the troposphere, and then it actually increases in temperature. Okay, really, really strange, really unique. Okay, and this is part of the reason why gases in the stratosphere won't mix with gases in the troposphere. Because if you think about a gas particle, which is really cold in the stratosphere, it makes the most sense for the particle to go up higher in the stratosphere to get warmer. So like if this particle is right here, which is very cold, it's going to move up because it knows if it can move up, it can get warmer, okay, which is kind of what it wants to do. Same thing if we look at a particle in the troposphere, it's really cold right here. Okay, so it's going to want to move down to get warmer. Okay, and so the convection cells for the stratosphere kind of look like this. You can think of they go up and down, up and down. Whereas in the troposphere they go the reverse direction, down then up, down then up. Okay, and so you'll never see this cross mixing between the stratosphere and the troposphere, because there's no reason for a particle right here to go down into the troposphere because it's actually getting colder. Okay, it makes more sense for it to go up. And so this temperature, this weird phenomenon of temperature increasing the stratosphere, okay, actually makes it so the stratosphere and the troposphere don't mix. Okay, hopefully that makes sense. Ask me some questions about that if that's still confusing. Okay, but that's why we don't have this mixing of the two spheres, because of this temperature difference in the stratosphere, this kind of reversing effect. Okay? All right, and then the last thing we talked about is a temperature inversion. Okay, and this is when temperature actually increases in the troposphere, okay, instead of decreasing. And so that's when the warm air gets stuck on top and kind of traps the cold air underneath it, which is the reverse or inverse of what you would expect of the normal conditions. Okay? And so instead of being, in the troposphere, usually it's colder on top, hotter on bottom because it's closer to the Earth's surface. Well, in a temperature inversion, you get the hotter on top and then the colder on the bottom. Okay? This hot air traps it underneath it. Okay? And so you really get this a lot in Utah because we have a lot of mountains. Okay? And the mountains kind of trap in that air. It makes it easier to trap the cold air underneath. And you can see this when we have this low, mist and fog. Okay. And that's when you can tell there's a temperature inversion. You get a lot in winter, and it can trap in a lot of particles, which makes the air kind of murky, you can think of. Okay. Which is why winter is kind of so miserable here, because of all this trapped air underneath. Okay. Because of the temperature inversions. Okay. And we watched this video that goes over kind of the effects and does a really good demonstration of what's happening. Okay, so I recommend watching that. Okay, but that is it for this part of the chapter. Here are some vocabulary words for you to write down and make sure you understand. Okay, but hopefully that all made sense. Let me know if you have any questions, and thank you for watching.